But tell me, what is it that causes, if we're talking about circular motion, okay, again, we're not talking about things that are spinning or rotating. That's rotational motion. That happens, there's a little bit of a more complex system that goes with that. But these are just things that are moving in a circular path. So before we can look at circular motion, we want to think about what happens in straight line motion, okay? What causes an object to move in a straight line? What has to have happened? Does it start from nothing? Do things randomly get put into motion without anything acting on it? No, what has to happen? Good, I have to apply a force, right? That's it. That's what I'm looking for. I have to apply a force, and the net force has to be in the same direction as the motion, right? So even if I have friction, or even if I have air resistance, if my net force is to the east, my object is going to move to the east, right? Even if I have friction, even if I have a brake, even if I'm applying a brake or something like that, if my net force is to the east, my object is going to move to the east. Okay? Now, how do I get an object into a projectile path, right? Do you remember what projectiles are? Projectiles, they fly through the air horizontally and vertically. So what has to happen to get my object started in a projectile path? Okay, good. It's got to have a horizontal and a vertical force, or otherwise I have to have a force applied at an angle, right? My force needs to be applied at an angle. So when we launch projectiles, we throw them, we kick them, we, launch them some upward at an angle, right? Or even if I'm on something higher like a platform, I could launch it downward at an angle, and I would still get an end projectile path. Okay? Objects moving in a circle have similar properties to projectiles in that they're moving in a curved type path, right? We're not really thinking about objects for this first part that are moving freely in a circular path. Normally they're going to be attached to something, right? There's going to be a string holding it in that circular path. There's going to be like a rod or something like that. It's going to keep it in its circular path. When we talk about planets, then we're going to have those things moving freely in a circular path, right? Can you think about what is holding planets in that circular path? Gravity. Good. That's what we're going to focus on the second part of this, is how the universal law of gravitation keeps things in that circular orbit and things like that. So, all right, here's where we're kind of getting into today's section, which is called uniform circular motion. What does it mean to be uniform? What's the word uniform mean in this context? It means an object that's moving at constant speed. So if I have uniform circular motion, as my object's moving in a circle, it's not speeding up or slowing down, right? It's moving at a constant speed. We'll use that V variable for speed, even though it's typically used for velocity. They're going to be a little bit interchangeable for us here, and I'll explain that here in a second. Okay? So we'll kind of use speed and velocity interchangeably here. Okay? Velocity has to have two parts to it. Do you remember what they are? Velocity is a vector, so what two things does it have to have? Direction and magnitude, right? It has to have the number and it has to have the direction. Both of those things make it a vector, and velocity is just an example of a vector, right? It's a type of vector. So I want you to think about something that's moving in uniform circular velocity, right? Uniform circular motion. It's moving in a circular path at constant speed, okay? Is it moving at constant velocity? No, why not? Kind of. If I'm moving at constant speed but not constant velocity, what's the one thing that's changing? Right? In uniform circular motion, the magnitude of the velocity remains constant, but the direction is changing, right? If I'm moving in a circular path, I'm constantly changing directions. And so I might be moving 6 meters per second, but my direction is ever changing, right? Because I'm moving in a circle. So we can have an object that's moving at constant speed, but not be moving at constant velocity. And that has to deal with the directional changes that happen in circular motion. Okay, so now let's keep going a little bit further with this. What is the definition of acceleration? What does acceleration mean? A change in, more specifically, velocity. Good. Change in velocity. So if we have a change in velocity, that automatically means we have acceleration. Okay, so this is a little tricky because usually we think of acceleration as speeding up or slowing down, right? And that's not really happening here. What's happening here is that we've got an acceleration due to the directional change, not the speed change, right? Not the magnitudinal change. So that's a little bit different than what we usually see with acceleration. Okay? Since velocity is changing continuously by direction, an object revolving in a circle is constantly accelerating even though the speed remains constant. Okay? So you can have acceleration without having a speed change. And that's something we haven't really seen before. Okay? Not something that I think should really throw us off for the chapter, but I do want you to understand that even though we're moving at a constant rate, we can still have acceleration. Okay, so I'm going to give you a new equation. You're going to get a couple new equations for this chapter. If you want to grab a new equation sheet, maybe go ahead and do that now. We can get a few together, and then we'll get you your new equation. All right, so here is our acceleration equation for what is called centripetal acceleration. Centripetal acceleration. And so this is the acceleration an object has when it's moving in circular motion, right? Uniform circular motion. So you will notice that for this equation for acceleration, it's not change in velocity, right? There's not a speeding up or a slowing down that's happened. So it's just the velocity of the object at that moment squared over, what do you think R stands for? What do you say? Radius, good. Radius, and it should be measured in meters. Velocity will be measured in meters per second. And then acceleration will still end up being measured in meters per second squared here. Okay? I would go ahead and put the little c next to that acceleration just so you know you're talking about a centripetal acceleration. All right, and an object moving in a circle with a radius r whose constant speed v has an acceleration whose direction is toward the center of the circle. Okay, so this has to deal with a lot of vector addition that I don't think we have to necessarily go into right now. But if I'm looking at an object who's moving in this direction, right? I'm moving in this direction. I'm moving. Okay, I get all the way over here. And let's say at this point, I am released from my circular path, right? Let's say right here, I get let go of. Would I continue to move in a circular path? Right? If right here my object is let go of, would my object continue moving in a circle? What would it do? Perfect. It would fly off in this direction, right? That's called tangent to the curve. If my object were removed from its circular path at that exact moment, it would not continue moving in a circle, right? It would fly off in the exact direction it was moving at that exact second in a straight line until something stopped it, right? That's Newton's first law, the law of inertia. An object in motion remains in motion until an outside force acts upon it. And so if I'm moving, 15 degrees north of west at that exact moment, that's where I'm going to fly off of, okay? And that phenomenon is called tangent to the curve. And so if you do some vector addition with this, velocity vector, you're going to end up with an acceleration that is toward the center of the circle. Okay, and I don't really need to go into the vector part of it, but our acceleration is always really going to be pointing inward in that way. Okay? And then let's think about this. As my radius of my circle increases, my acceleration is going to decrease. Okay? And I want you to kind of think about what that might look like. If my... let's see here. if my circle is really small, for every second that goes by, I'm covering a really big chunk of my circle. Agreed? Right? For every second that goes by, I'm covering a really big portion of my circle. But if my circle increases, right, my radius gets larger and I'm still moving the same, meters per second, I'm covering a lot smaller portion of my circle, right? So as my radius increases, it should make sense to us that our acceleration is decreasing, right? Not only does it prove it mathematically since radius is in our denominator, but we should be able to think about the fact that we're going to cover a lot smaller chunk of our circle per second as our radius increases there. Okay? All right. These are two new kind of concepts here called period and frequency. I'm not sure that we've talked about these yet in here. If we have, it's just slipping my mind. But period and frequency help describe to us a couple different things. So they will talk. They're gonna relay to us information about how many revolutions we're making per second and the reciprocal of that. So revolutions, you can also think about that as like, what's another word for revolutions? Rotations. That's a good one. Okay. Rotations per second, you could think about it that way. It's how many times you go around the circle in 1 second. That's what frequency is. Okay, when we talked about waves, I think we did period and frequency a little bit. Okay, but this is rotations per second is frequency, and then the reciprocal of that is called the period. And so this is how much time it takes per revolution, or how much time it takes to complete one rotation. So if frequency is revolutions per second, then period is seconds per one revolution, right? They're complete reciprocals of one another. And so this equation does need to go on your equation sheet. Okay, you could also write it F equals 1 over T since they're true reciprocals of one another. Either way is fine. You probably don't have to have both, but you're welcome to write both if you really prefer. What is that top equation for? It has to do with the circle. The what? The circumference. Good. The circumference. That's okay. This top one is the circumference of the circle. Tell me, why would it matter to us to be able to calculate the circumference of a circle in this chapter? Why is it important to us? If we're talking about items moving in circular motion, why do we need to be able to calculate the circumference? Say it again. No, you're right. It's how far we're traveling, right? It's telling us the distance we're traveling, right? And so if I look at my equation for velocity, velocity is usually distance over time, right? Agreed? Velocity is usually distance over time. And so when we talk about circular motion, we put our equation to say the circumference of our circle, or the distance for one revolution, over the time it takes to complete one revolution, the period. Right? And so that's our equation for the velocity of an object, or speed of an object moving in circular motion. So I would put this one on your equation sheet as well. We're going to be able to kind of mix and match and combine lots of these equations. But this allows us to look at how far we travel in one revolution and then how long it takes us to make one revolution. Okay, make sure you see that T is period, capital T is period. It's still measured in seconds though, right? So this is still going to be measured in meters per second. Okay, because circumference is going to be measured in meters if radians is in meters. Okay, you guys ready to try one here? A runner moving at a speed of 8.8 meters per second rounds a bend with a radius of 25 meters. What's the centripetal acceleration of our runner? Centripetal acceleration. So what equation am I solving? Sorry, I'll give you a second. Go ahead and get written down what you want, and then we'll... All right, so centripetal acceleration, our equation looks like this. AC equals v squared over r. This is very just simple, right? Our velocity is 8.8. We want to square that over 25 meters. And that gives me a centripetal acceleration of about 3.09, maybe 3.10 if you round up, that's fine. Okay, and our our units are still meters per second squared. We're going to be able to attach Newton's second law, which usually says net force equals mass times acceleration. And now we're going to be able to apply it to the centripetal motion. Okay, and so this is called now centripetal force. Centripetal force. You could label it FC if you wanted to for centripetal force, since you've got a centripetal acceleration there. If you prefer to do it that way, you can. But we solve for it exactly the same way that we solve for the net force. Okay, so you are welcome to label it either way. I'm not really sure which way I label it. I kind of go back and forth, I guess. But we're solving for it the same way that we solve for the net force. Okay, this has got to be centripetal acceleration. What happened between this equation and this equation? From the first to the second, what was the only thing that happened? Right, we substituted the equation for acceleration in for AC. Right, AC equals v squared over r. So we just did the substitution from one to the next. If you'd like to put both of those equations on your equation sheet, you are welcome to. Or if you just want the first one, you know that you can do that substitution whenever you need to solve for A. Okay, or you could solve for A separately and then plug it into, that would work fine. Okay, this says a 13-gram rubber stopper is attached to a 0.93 meter string. The stopper is swung in a horizontal circle, making one revolution in 1.18 seconds. Find the tension force exerted by the string on the stopper. Let's just look at kind of a bird's eye view of what this would look like. Okay, a view from the top. There's my circular path. Here's my string. It says the string is 0.93 meters. Do I need to cut that 0.93 meters in half or not? Right? Do I have to cut that 0.93 meters in half to find my radius? No, right? If this distance is 0.93 meters, when I do my circle, that is my radius, right? That's going to be my whole entire radius. I don't have to cut it in half to find the radius. Okay? So that means this distance is 0.93. Okay? I want to find the tension force exerted by the string on the stopper. In this case, my tension force is really the only thing acting, right? So I could say that my centripetal force is equal to my tension force, right? In horizontal problems like that, tension is really the only thing that we have making it go, right? As long as that string has some movement in it and some tension in it, it's going to keep going. So, another way to solve for FC is to take mass times centripetal acceleration equals my tension force, right? Do I have centripetal acceleration? Not really yet. Okay, let's start writing down what we do have. I have mass, but what do I need to do to that mass? It's got to be in kilograms, so 0.013 kilograms. It says I make one revolution in 1.18 seconds. So is that my period or is that my frequency? It's measured in seconds. So that's period, right? T is seconds, so 1.18. That'll be something that you really need to focus on and think about, because some people will mix up period and frequency pretty often, okay? And then I have a radius of 0.93. Can I solve for my velocity? Right, velocity equals 2 pi r over t. Do I have all those things? Yeah, that's kind of tricky because it doesn't mention anything here about velocity, right? But we're going to have to end up solving that in order to get to that point, right? So let's go 2 times pi times r over t. You can use the pi button on your calculator, or you can just plug in 3.14. It doesn't really make a difference. We'll have a little bit of a rounding issue, but not too much. Make sure you do hit enter when you do the numerator. But I think I get a velocity here of 4.95 meters per second. Okay? And so now, if I'm going to go up here and look at my equation for force, m times AC, what I should really do is just go ahead and plug in my velocity there instead of solving for A first, right? It doesn't really matter, but if I was going to do this, I could say m times v squared over r, right? That's AC right there, equals my tension force. Does that make sense? I just kind of substituted that in for AC. So I would say 0.013 times 4.95 squared over r, which was 0.93, equals my tension force. So go ahead and do the interior of those parentheses first. And I get a tension force equal to 0.343 newtons. So in this object, I want you to look at our circular pattern again. Now, this time we're not looking at it from above, we're looking at it from the side. Agreed? Okay, if it's a vertical object, I'm looking at it from the side now. And I want to know what's happening at the top of my motion. So here's my object here at the top. What's moving toward the interior of the circle here? Right, I've got a tension force. What else do I have that's moving in that direction? I have gravity, right? Gravity's acting in that downward direction. Do we agree with that part? If I'm looking at something on the bottom of my motion, I've got tension moving this way, and I would have gravity moving downward, right? Does that kind of make sense? But right now I'm looking at the top of my motion. Okay, I want to know the minimum speed. I want to know the minimum speed. So I'm looking for velocity, right? That's what I want to look for. I have mass. I have my radius, 1.1. Okay. And so I want you to kind of think about what's happening here, okay? If I set up my net force equation or my centripetal force equation, right, I would say I've got tension plus gravitational force, right? And why am I adding them together? They're both moving in the same direction, right? Both moving in the same direction. Something that I maybe should have talked about before is that we always consider the center of the circle the positive direction. Okay, and I don't think I mentioned that before. But since acceleration is moving toward the center of the circle, we count the center of the circle the positive direction. So that's why we're keeping these both positive. We're not doing 0 minus that. Okay, so center of the circle is our positive direction. We're going to do tension plus gravity. If I want to find the minimum speed, that means that I want my tension force to essentially be 0. right? I want my tension force to be 0 because I don't want any tension in there, but I don't want negative tension either, right? I want it to be just enough to keep it in motion. So my tension force is 0. How do I always solve for Fg? Mass times what? 9.8. And then what can I substitute here for centripetal force to get what I need? I can do mass times v squared over r, right? Even though I'm going to go ahead and plug in some numbers there because I'm really just solving for v. Yeah, go ahead. Yes, thank you. There we go. All right, so that means over on the left side, I'm also going to do 0.15 times v squared over 1.1 equals 0.15 times 9.8 is 1.47. Okay, so to get v squared by itself, I'm going to go ahead and divide by 0.15. There's a couple of different ways you could go about this for algebra, but I'm going to go ahead and do it this way, divide by 0.15. I don't know why I just did that. I know it's going to equal 9.8. Okay, equals v squared over 1.1. So what's my next algebra step? Times 1.1 times 1.1, and that gives me 10.78 equals v squared. And so to get v by itself, what do I need to do? Square root both sides. And so that means my minimum speed is 3.28 meters per second. 3.28 meters per second. That's the minimum speed I'm going to have to go if I wanted to stay in my circular path. And the trick with that one was that we assigned tension a value of 0, right? When I'm looking for minimum speeds, my tension would have a value of 0. If I was looking for the maximum speed, I would have to have a tension value that was given to me, right? I would have to have another piece of that puzzle. Calculate the tension in that same cord, assuming the ball is moving twice the speed of part A. Okay? Calculate the tension in the cord at the bottom of the arc, assuming it's moving twice as fast as it was at the top. Okay, now let me just tell you, that's not like a rule. It's not always moving twice as fast at the bottom as it is at the top. That's just for this particular example, okay? So I want to know how fast, I want to know what's the tension in my cord here, right? That's what I'm solving for. What's the tension? But in this case, I've got gravity here that's working against that, right? Tension's pulling it up, gravity's pulling it down. So as I set up my centripetal force equation, I would say tension, which is moving toward the center of the circle, minus gravity, because gravity at this time is moving away from the center of the circle. Okay, and I'm looking for my tension force. Okay, so what can I substitute here for Fc? I can do mass times v squared. So what am I going to, how do I know my velocity? Yeah, it's just twice that 3.28. So I'm going to take 3.28 times 2, and I get 6.56. So let's just round up to 5.7. I'm going to square that over my radius. My radius does not change. Tension force minus mass times 9.8. Right? So we're kind of combining, going back here to our net force equations and all that kind of stuff to get to look at centripetal force. Okay, so this comes from multiplying my velocity from part A by 2, right? Because it says, assuming that the ball is moving twice the speed of part A, right, of what we just solved for. So that's where my velocity comes from. That's V. Okay, and so if I do that whole left side of the equation, I get 5.88 equals my tension force minus 1.47. And then I'll add that to the other side. Okay, and I get a value of 7.35. And what's my unit here if this is a tension force? Newtons. Yep, newtons.